You ever stop and think about the fact that in 1970, a group of engineers in Dearborn, Michigan built a pushrod V8 that was putting out somewhere around 900 horsepower, and then their own company told them to pretend it never happened? Not because it blew up, not because the heads cracked, not because the math was wrong, because it worked too well at exactly the wrong moment in American history. That is the story of the Tunnel Port Boss 429, and it is one of the most fascinating, frustrating, and revealing stories in the entire history of American performance engineering. This is legacy motoring, and I spend way too much time thinking about engines that never got their chance. If you're someone who obsesses over the buried history of American muscle, the engineering decisions that got made behind closed doors, and the cars and engines that almost changed everything, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. Alright, let me set the stage for you, because you cannot understand why this engine was such a problem unless you understand what Ford was doing throughout the entire decade of the 1960s, and what they were doing was winning, aggressively, expensively, and occasionally right up against the ragged edge of what the rulebook technically permitted. Ford's Total Performance campaign kicked off in 1962, and the concept behind it was as simple as a sledgehammer. Win races on Sunday, sell cars on Monday. Henry Ford III wanted his company associated with speed, with dominance, with the kind of visceral excitement that made a man walk past a Chevrolet dealership and keep going until he found a blue oval on the building. And it worked. It worked spectacularly. Ford won Le Mans 4 consecutive times starting in 1966. They put the GT40 program together with a kind of ruthless corporate determination that is difficult to overstate. Ferrari had embarrassed Ford at the negotiating table, and Henry Deuce responded by spending whatever it took to beat Ferrari at their own game, on their own turf, in front of their own fans. That is a level of competitive spite that borders on the poetic. But Le Mans, as significant as it was on the world stage, was not where Ford moved the most metal in America. NASCAR was the crown jewel. Stock car racing had a cultural penetration in this country that European endurance racing simply could not match, particularly in the South and the Midwest, where Ford was selling enormous volumes of vehicles. A win at Daytona translated directly into showroom traffic in ways that a win at Le Mans never quite could. A buyer walking into a dealership in Charlotte or Memphis or Birmingham did not care what happened in France. He cared what happened at Daytona. He cared what happened at Talladega. He cared about the cars he saw running flat out on those high banks every weekend, and he wanted something connected to that experience sitting in his own driveway. Ford understood this with perfect clarity, and so they poured resources into NASCAR engine development and aerodynamic programs that left their competition scrambling. Championship after championship, drag strips across the country saw blue oval domination. The Total Performance era was not a marketing slogan. It was a corporate philosophy backed by real engineering and real money. Now, here is the thing about winning at NASCAR, specifically at the superspeedways. You did not just need a powerful engine, you needed a specific kind of powerful engine. Daytona, Talladega, these tracks demanded sustained high-speed operation for hundreds of miles without mechanical failure. Engines ran at high RPM continuously, not in bursts, not for a quarter mile at a time, for hours. Cooling systems were stressed to their absolute limits. Oil pressure had to remain consistent through the enormous lateral loads generated by banking at speed. The engine that could win Daytona had to be both brutally strong and mechanically intelligent. It had to make power, and it had to survive making that power under conditions that would destroy anything not specifically engineered for the task. In 1968, Ford introduced the Boss 429 specifically to meet NASCAR's homologation requirements. Here is how that worked. NASCAR's rules required that any engine a manufacturer wanted to race had to be available in a production vehicle sold to the public. The minimum production threshold was set at 500 units. Build at least 500 street cars with the engine, and you could race it. Ford took the Boss 429 and shoehorned it into Mustangs. Clarcraft, the specialty shop Ford used for projects that required more flexibility than a normal assembly line could provide, handled the installation work. The engines were physically wider than the standard big block due to the hemispherical combustion chamber head design, and fitting them into the Mustang engine bay required significant modification to the shock towers and inner fender structures. These were not simple bolt-in installations. They were engineering exercises and packaging compromise. The resulting cars were sold through select dealers, technically street legal, technically meeting the letter of the homologation requirement. The official power rating stamped on the Boss 429 in street trim was 375 horsepower. Now, I want you to hold that number in your mind for a moment because we're going to come back to it. And when we do, you're going to understand exactly how much creative fiction was involved in American horsepower ratings during this era. That 375 horsepower figure was, to put it charitably, a work of corporate imagination. Independent dynamometer testing of stock Boss 429 engines consistently produced results considerably north of that number. Factory race-prepared versions were pushing well past 500 horsepower by the 1969 racing season. The official rating existed for one reason and one reason only: to keep insurance premiums from becoming completely unmanageable and to avoid attracting the kind of attention from federal regulators that nobody in Detroit wanted. Every manufacturer was doing this. General Motors was doing it, Chrysler was doing it, Ford was doing it. It was an industry-wide arrangement, an unspoken agreement that the numbers on paper would bear only a passing resemblance to the numbers on the dyno. Everyone in the business understood the game. Nobody discussed it at shareholder meetings. Nobody put it in writing if they could avoid it. But even with the standard Boss 429 delivering genuinely impressive performance in race trim, Ford's engineers were not satisfied. Satisfaction was not in their professional vocabulary during this period. By the end of the 1969 season, the competitive pressure from Chrysler's Hemi program and from the ever-increasing demands of superspeedway racing had created an environment where good enough was not a concept anyone was entertaining. Ford's racing engine group began developing a revised cylinder head design that would take the already aggressive port layout of the Boss 429 and push it into territory that no production-based American pushrod engine had ever explored. And this is where the tunnel port concept enters the story. This is where it gets really interesting. Here is what most people do not realize about cylinder head design. Having big ports is not automatically better. It seems intuitive that a bigger opening would let more air in, and more air means more power. And at high RPM, that intuition is essentially correct. But at lower engine speeds, an oversized port actually hurts performance. The air-fuel mixture moves too slowly through the passage, loses velocity, and fails to fill the cylinder efficiently. Think of it like a garden hose versus a fire hose. If you have low water pressure, a garden hose gives you a strong, useful stream. Connect that same low-pressure source to a fire hose, and you get a pathetic dribble. The cross-sectional area of the passage has to match the volume and velocity of what is flowing through it. This is the port velocity problem, and it is one of the fundamental challenges of engine design. Solving it requires matching the port dimensions to the engine's intended operating range. Ford's engineers understood this completely. They also understood that at NASCAR superspeedway speeds, where engines ran consistently above 7,000 RPM for extended periods, the calculation inverted entirely. Up there, in that operating range, you wanted maximum flow, the largest possible pathway for air and fuel to enter the cylinder. Because at those RPM levels, restriction was the enemy. Any unnecessary narrowing of the intake tract cost you charge density, and lost charge density meant lost power. Every cubic centimeter of airflow you could gain at 7,500 RPM translated directly into measurable horsepower on the dyno and measurable speed on the track. The problem was packaging. A conventional pushrod engine has inherent constraints on how large you can make the intake ports. The pushrods themselves, the mechanical linkages that transfer camshaft motion to the rocker arms that open the valves, have to pass from below the cylinder head to above it. They occupy physical space, space that is adjacent to or conflicts with the intake port pathways. You can only make the ports so wide before you run into the pushrods. You can redesign the rocker geometry, you can adjust angles, you can optimize within the existing architecture. But at some point, the pushrods become a hard physical limit on port size. The tunnel port solution was either brilliant or completely audacious, and honestly, it was probably both. Instead of routing the pushrods around the intake ports, Ford's engineers ran them through the ports, directly through. Each intake port had a tube cast into it, running through the center of the passage, and the pushrod passed through that tube. This radical repositioning freed up the surrounding port volume. The ports could be made dramatically wider and more optimally shaped because the pushrods were no longer constraining the external port geometry. They were contained within their own sealed passages running through the middle of the airflow path. When you look at a tunnel port head for the first time, it genuinely stops you. There is a tube running through the middle of the intake port. Right through the center of the path the air-fuel mixture needs to travel to reach the combustion chamber. It looks wrong. It looks like a manufacturing error. It looks like someone drilled a hole in the wrong place and then tried to fix it by shoving a tube through it. It was not a mistake. It was a deliberate, calculated engineering decision that accepted known theoretical penalties in exchange for massive high RPM flow advantages. Now, you might be thinking, wait, does not a tube running through the middle of the airflow path create turbulence and disrupt the charge? Yes, it does. The engineers knew this before they built the first prototype. They ran extensive flow bends testing to characterize the disruption precisely. They measured the pressure differential, the flow loss, the change in charge velocity distribution across the port cross-section. They quantified exactly how much the tube cost them at every point in the RPM range and at every increment of valve lift. And they concluded that the gains outweighed the losses at their target operating range. At low RPM, the tube was a meaningful penalty. At racing RPM, the increased total flow capacity more than compensated for the localized disruption. The net result was substantially more airflow into the cylinder at the RPM levels where these engines would actually operate in competition. Look, this is the kind of engineering decision that separates people who build good engines from people who build historically significant ones. The willingness to accept a known compromise in one area because you have calculated, tested, and confirmed that the gains in another area are larger. It is not intuition, it is not guesswork, it is disciplined analysis applied to an unconventional idea. And it worked. The flow bench numbers confirmed it. The dyno numbers confirmed it. The tunnel port heads flowed significantly more air at high valve lift than the standard Boss 429 heads, which were themselves already among the best flowing production-based heads in the American automotive industry. Ford developed these heads through 1969 with increasing urgency. The competitive landscape was not standing still. Chrysler's Hemi program was formidable. The other manufacturers were pushing their own development programs. Staying ahead required continuous advancement. By late 1969, the tunnel port engine program had produced results that were, by any reasonable standard, extraordinary. In configurations that remained within NASCAR's technical regulations, the engine was producing somewhere in the range of 600 to 700 horsepower. With more aggressive development, optimized carburation, and no restrictions from the racing rulebook, the engineers were seeing higher numbers, significantly higher. Estimates from personnel directly involved with the program placed the potential ceiling close to 900 horsepower on full race preparation with period-correct racing fuel. Some accounts from people who were in the room when the engines were tested suggest numbers that exceeded 900. The precise figures are disputed, and they are disputed partly because Ford was not carefully documenting programs it was not officially running. There was a deliberate informality to the record-keeping that served a corporate purpose. If you do not write it down, it is harder for anyone to prove it happened. What is not disputed by anyone with knowledge of the program is the direction. This engine was producing power numbers that had no precedent in production-based American pushrod engine development. And that combination, extraordinary power from a block that carried at least nominal production credentials, was about to become a very serious problem on the executive floor in Dearborn. Here is where the story shifts from engineering triumphs to corporate calculation. And this is the part that makes the tunnel port Boss 429 such a compelling piece of automotive history. Because the engine did not fail. The program was not canceled because the heads cracked or the ports did not flow or the dyno numbers disappointed anyone. The program was killed by forces entirely external to the engineering itself, and understanding those forces tells you as much about 1970s America as it does about engine design. NASCAR's homologation requirement existed for a specific and important reason. It was designed to maintain some meaningful connection between what raced on the track and what sat in dealership showrooms. A manufacturer could not simply build a pure prototype racing engine, install it in a handful of vehicles assembled in a back shop somewhere, and claim those vehicles represented a production model available to the buying public. The minimum production threshold, that 500 unit number, was the mechanism intended to enforce this connection. If you wanted to race it, you had to prove you could build it and sell it at a scale that qualified as genuine production. Ford had already stretched this requirement with the standard Boss 429. The car craft operation that stuffed those engines into Mustangs was not a normal assembly line process. It was a specialized, low-volume, expensive undertaking that satisfied the letter of the rule while taking considerable liberties with its spirit. NASCAR had accepted it. The cars existed. Customers could buy them. The boxes were checked. The tunnel port heads pushed the interpretation considerably further. To homologate the tunnel port engine for 1970 competition, Ford would have needed to produce and sell the required minimum number of street vehicles equipped with these heads, and the problems with that requirement stacked on top of each other immediately. The tunnel port heads were not simple to manufacture. The geometry was complex. Casting a cylinder head with tubes running through the intake ports required more sophisticated tooling and more demanding quality control than the standard Boss 429 heads, which were themselves already more complex than typical production castings. Machining tolerances for the pushrod tubes were tight. The tube had to be properly sealed against the intake charge while allowing the pushrod to move freely within it. Any failure in that seal meant pressurized air-fuel mixture leaking around the pushrod, which meant both a performance loss and a potential fire hazard. Producing the required number of these heads for installation in street vehicles on a racing program timeline would have required significant capital investment in tooling that served no other purpose. These were not heads you could repurpose for a production engine line. They existed for one reason: to go fast at Daytona. Every dollar spent on tunnel port production tooling was a dollar that generated zero return outside of the racing program. That investment might have been justifiable if the tunnel port program had a long and profitable future ahead of it. By late 1969, the evidence was mounting that it did not. The automotive industry and the insurance industry were locked in a loud, public, and increasingly consequential argument about high-performance vehicles. Insurance companies had been watching horsepower numbers climb steadily throughout the 1960s. They had also been watching claim rates on high-performance vehicles climb right alongside them. Young men buying muscle cars were, statistically, getting into more accidents and filing more expensive claims than buyers of comparable standard vehicles. The insurance industry responded with dramatically increased premiums for high-performance models. Some insurers were refusing to write policies at all for certain engine and vehicle combinations. If you were a 22-year-old trying to insure a Boss 429 Mustang in 1970, you were discovering very quickly that the sticker price of the car was the least of your financial problems. The annual insurance premium could approach or even exceed the car payment itself. This was not a minor inconvenience. This was a structural threat to the entire muscle car market segment. A car that customers cannot afford to insure is a car that customers cannot buy, regardless of how much they want it. Dealer lots were beginning to show the effects. High-performance models that had moved briskly 2 years earlier were sitting longer. The economics of the muscle car were shifting under the feet of every manufacturer simultaneously. Beyond insurance, political pressure from Washington was real, growing, and showing no signs of reversing course. Congressional hearings were examining automotive safety with an intensity that would have been unthinkable a decade earlier. Ralph Nader had published Unsafe at Any Speed in 1965, successfully attacking General Motors over the Corvair's handling characteristics, and the resulting cultural and legislative environment had permanently changed how lawmakers and regulators thought about automobile safety and manufacturer responsibility. The National Traffic and Motor Vehicle Safety Act of 1966 had established federal safety standards for the first time. The regulatory apparatus was in place, and it was expanding. General Motors had already read the writing on the wall. In a move that was equal parts prudent and preemptive, GM announced an internal corporate policy limiting production car engines to approximately a 1-to-1 ratio of horsepower per 10 pounds of vehicle weight. It was voluntary restraint, designed to demonstrate corporate responsibility and to get ahead of potential mandatory regulations that could have been more restrictive. The signal it sent to the rest of the industry was unmistakable. The direction of travel was toward less power, not more. The era of escalation was ending. Into this environment, Ford's racing engineers wanted to homologate an engine producing somewhere in the vicinity of 900 horsepower, an engine that would need to be installed in street-legal vehicles and sold to the general public to satisfy a racing rulebook requirement. An engine whose very existence would be a billboard advertising exactly the kind of excessive automotive performance that insurance companies were lobbying against, that Congress was holding hearings about, and that the industry's largest manufacturer had just publicly committed to restraining. You can imagine how that conversation went in Dearborn. You can picture the meeting. The engineers presenting flow bench data and dyno sheets, the executives looking at actuarial tables and congressional hearing transcripts and letters from insurance industry lobbyists. Two groups of smart people looking at the same situation from completely different angles and arriving at completely different conclusions about what the right course of action was. The executives made their calculation. They looked at the tooling investment. They looked at the insurance environment. They looked at the political landscape. They looked at the competitive picture, where the entire muscle car category was beginning to contract at its commercial edges. They looked at whether Ford was going to continue its full factory NASCAR commitment beyond 1970. And the answer to that question was increasingly looking like no. They said no to the tunnel port program. Not loudly, not in a dramatic boardroom confrontation that makes for good cinema. The decision happened the way most significant corporate decisions happen, quietly, through budget allocations that did not include funding for the tunnel port tooling, through meeting agendas that did not list a program for discussion, through an institutional turning away from something that had become inconvenient. Nobody wrote a memo saying kill the tunnel port program, or if they did, it has never surfaced publicly and probably never will. The program simply stopped receiving support, stopped appearing in planning documents, and stopped existing as an active development effort. The engines that had been built were not immediately gathered up and destroyed. Ford did not send someone around with a sledgehammer, despite what some of the more dramatic retellings of this story might suggest. Some tunnel port engines and components found their way into racing programs that continued on reduced or no factory support after Ford's official withdrawal. Some pieces went into engineering storage at Ford facilities. Documentation of what happened to specific units is incomplete, which is itself informative. Ford was not maintaining careful records of a program it was officially not running. You do not create a paper trail for something you want to be able to deny. Now let us talk about what the tunnel port Boss 429 actually was mechanically, because the engineering deserves considerably more than a summary. If you are going to appreciate why this engine matters, you need to understand the specifics of what Ford's engineers accomplished at every level of the assembly. The foundation was the standard Boss 429 block, cast iron construction, 429 cubic inches of displacement, which translates to 7.0 liters in modern terms. Bore measured 4.36 inches. Stroke was 3.59 inches. That bore-to-stroke ratio, significantly over square with the bore diameter wider than the stroke length, was a deliberate design choice with specific performance implications. An over-square engine has shorter piston travel per revolution, which means lower piston speeds at any given RPM. Lower piston speeds translate directly into reduced mechanical stress on the pistons, wrist pins, and connecting rods. This means the engine can safely rev higher before the reciprocating forces become destructive, and revving higher was the entire point of this engine's existence. Every design decision in the Boss 429 block started from the premise that this engine was going to live at sustained high RPM in the most demanding racing environment in American motorsport. The block used 4-bolt main bearing caps on the center 3 main journals. This is a racing specification detail that tells you exactly what Ford intended from the moment the first block was poured. A standard production engine uses 2-bolt main caps, which are perfectly adequate for street use and moderate performance applications. 4-bolt mains distribute the clamping load across twice as many fasteners, dramatically increasing the main cap's resistance to the tendency to shift or walk under the enormous reciprocating forces generated at sustained high RPM operation. When you are turning 7,500 RPM for 3 hours at Daytona, the forces trying to move those main caps are extraordinary. 4 bolts hold better than 2. It is that straightforward. The crankshaft was forged steel, not cast. This distinction matters enormously in a high-performance application. Forging subjects the steel billet to enormous compressive forces that align the internal grain structure of the metal, producing a part that is significantly stronger and more fatigue-resistant than a casting of identical external dimensions and composition. A forged crankshaft absorbs the torsional vibrations and cyclic stresses of sustained high RPM operation, without developing the fatigue cracks that will eventually propagate through a lesser component and cause catastrophic failure. When your engine is your racing career and your engine builder's reputation and potentially the physical safety of the driver and everyone near the track, you use a forged crank. There is no discussion. Connecting rods were forged steel. Same logic, same reasoning, same refusal to compromise on the components that exist between the explosions happening in the combustion chambers and the rotation happening at the flywheel. Pistons in race configuration were forged aluminum, lightweight to reduce reciprocating mass and allow higher safe RPM, and strong enough to withstand the cylinder pressures generated by the compression ratios these engines ran. And those compression ratios were meaningful. In full race trim, the Tunnel Port Boss 429 ran compression ratios in the range of 10.5 to 11.5 to 1, depending on the specific build and the specific application. For context, a typical American passenger car engine of this era ran around 8.5 to 9.0 to 1. The Boss 429's ratio was substantially higher, and that difference translated directly into thermodynamic efficiency and power output. Higher compression extracts more energy from each combustion event by expanding the burning gases through a greater volume ratio. The penalty is that high compression engines require high octane fuel to prevent detonation, the uncontrolled self-ignition of the air-fuel charge ahead of the flame front. Detonation produces enormous localized pressure spikes that will destroy pistons, bearings, and ringlands with terrifying speed. In 1970, with leaded racing fuel readily available, providing octane ratings well above 100, managing detonation in a high-compression racing engine was a solved problem. But the transition to unleaded fuel was already on the horizon. The very fuel these engines were designed to burn was becoming a regulated substance. One more element of brutal timing in a story that is defined by them. The cylinder heads themselves deserve detailed attention because they are the heart of what makes the tunnel port program historically significant. The standard Boss 429 heads were already remarkable by the standards of production-based American engines. Intake valves measured 2.28 inches in diameter. Exhaust valves were 1.90 inches. These are large valves by any standard, providing substantial flow area when fully open. Port design favored high RPM airflow over low-speed charge velocity, a deliberate choice reflecting the engine's intended operating environment. Combustion chamber geometry was semi-hemispherical, positioning the spark plug centrally in the chamber with large intake and exhaust valves arranged on opposing sides. This geometry promotes efficient flame propagation from the central ignition point outward across the chamber, reducing the tendency toward end gas detonation and allowing more aggressive ignition timing. The tunnel port heads retained this fundamental architecture and restructured the intake port geometry in the ways I have described. Ports widened substantially. Cross-sectional area of the intake tract increased dramatically. Pushrod tubes cast directly into the port passages, sealed against the incoming charge, sized as small as practical while allowing pushrod passage with appropriate clearance for thermal expansion and mechanical movement. Flow bench testing confirmed that the tunnel port heads delivered significantly more airflow at high valve lift compared to the standard heads. At low lift values, the advantage was smaller, and the proportional disruption from the pushrod tube was more significant relative to total flow area. At the lift levels and sustained RPM of NASCAR superspeedway racing, the tunnel port design was measurably and meaningfully superior. The exhaust side received parallel development attention that is often overlooked in discussions of the tunnel port program. An engine is fundamentally a pump. It draws in charge, compresses it, extracts energy from combustion, and expels the spent gases. The engine pumps only as well as its most restricted point allows. Improving the intake side while neglecting the exhaust side would have created a bottleneck that limited the gains from the tunnel port intake design. Ford's engineers worked both sides simultaneously. Exhaust ports were enlarged and their flow characteristics revised to ensure the engine could expel combustion byproducts as efficiently as it ingested fresh charge. Ignition systems for the race builds were high-output units specifically engineered for the demands of this application. At the cylinder pressures and RPM levels these engines generated, reliable ignition of the compressed charge becomes increasingly challenging. The spark has to jump the plug gap against higher resistance. The time window for the spark event at high RPM shrinks, and the ignition system must deliver consistent energy thousands of times per minute without degradation. Timing curves were calibrated for racing fuel characteristics, running more aggressive advance than any street tune would safely allow. Oiling systems and race specification used high-volume pumps and, on the most serious builds, dry sump systems. Here's why that matters. A conventional wet sump system stores oil in a pan bolted to the bottom of the engine. Under sustained lateral acceleration, the kind generated by running at 190 miles per hour through the banking at Daytona for lap after lap after lap, the oil sloshes to one side of the pan and away from the pickup tube. Even momentary oil starvation at those RPM levels can wipe bearings and destroy an engine in seconds. A dry sump system uses an external reservoir and a scavenge pump to continuously evacuate oil from the engine and return it to the reservoir, ensuring consistent oil supply regardless of lateral forces. It also allows a shallower oil pan, lowering the engine's center of gravity, which improves the car's handling characteristics. Both advantages are significant in competition. The fully assembled race engine, with every component optimized for its intended application, produced power numbers that were extraordinary for 1970 and would remain impressive by any standard for decades afterward. Conservative estimates drawn from available documentation and first-hand accounts of the engineers who were present place competition legal output at 600 to 700 horsepower. Full development output, without racing restrictions, with aggressive carburation setups, optimized ignition timing, and the best available racing fuel, was estimated by program participants at approaching 900 horsepower. Some accounts suggest the number was higher. For context that makes those numbers land properly, a 1970 Boss 429 Mustang in street configuration weighed approximately 3,500 pounds. At 900 horsepower, that delivers a power-to-weight ratio of roughly 0.26 horsepower per pound. That number shows up in modern supercar specifications, cars costing seven figures, cars built with 40 years of additional metallurgical, computational, and aerodynamic knowledge. It had absolutely no business existing in a 1970 American production-based vehicle. Ford's engineers had built something that the era they built it in was simply not prepared to accept. The consequences of the tunnel port program's cancellation played out across multiple levels simultaneously, and each level tells you something different about what was happening in American automotive culture at that precise moment. On the immediate racing front, the 1970 NASCAR season was the last in which Ford operated as a fully committed factory effort. The tunnel port engines that did see limited competition in various forms demonstrated the program's raw potential clearly. The performance was there, the capability was proven, but the corporate decision had been made before the checkered flag fell on the season's final race. Ford's racing budget was cut dramatically after 1970. The total performance era was ending, not because Ford could not win, but because the cost-benefit analysis of winning no longer justified the expenditure in an environment where the commercial rewards of racing victories were diminishing alongside the muscle car market that had fueled them. The engineers who had spent years developing the tunnel port heads, who had solved packaging problems and flow dynamics challenges that no one else in the industry had attempted, found themselves reassigned to other projects or separated from the company entirely as the racing department contracted. Careers that had been built on competition engine development were redirected or ended. The institutional knowledge those engineers carried, the practical understanding of what the tunnel port design could do and how it behaved under various conditions, began to disperse. Physical engines and heads scattered in various directions through channels that were not systematically documented. Some components went into Ford's internal engineering storage, where they sat in warehouses and were occasionally rediscovered years or decades later by people who recognized what they were looking at. Some pieces were acquired by independent racers who continued competing with Ford Power after the factory withdrew its support. Some ended up in private collections through paths that were informal at the time and have grown murky with the passage of decades. No systematic effort was made to catalog what existed or to preserve the development work as a coherent historical record. Things got distributed, repurposed, lost, and occasionally found. On the broader level, the tunnel port program ended at exactly the moment the entire era it belonged to was ending. And it is important to understand that the same forces that killed the tunnel port killed the entire category of cars that program was designed to serve. 1971 brought meaningful reductions in compression ratios across the American automotive industry, driven by the approaching mandatory transition to unleaded gasoline. High compression ratios require high-octane fuel. Tetraethyl lead was the primary octane booster in gasoline, and it was being phased out because it destroyed catalytic converters, which were themselves being mandated to reduce exhaust emissions. Remove the lead, lose the octane, and an engine designed around 11-to-1 compression would detonate destructively on the new fuel. Manufacturers had no choice. Compression ratios came down, power numbers dropped. Then they kept dropping. 1972 brought new SAE measurement standards, shifting horsepower ratings from gross to net figures. Gross horsepower measured the engine on a dyno without accessories, without an air cleaner, without an exhaust system. Net horsepower measured it as installed in the vehicle with all accessories and restrictions in place. Already declining actual power numbers now looked even worse on paper. Customers noticed. The perception of performance decline was amplified, beyond the already real mechanical decline. Then came October of 1973 and the OPEC oil embargo, and within weeks, the entire commercial logic of high-performance American automobiles inverted completely. Fuel economy went from a secondary consideration to the dominant consumer concern almost overnight. Long lines at gas stations, rationing, price spikes that made filling the tank of a big block anything feel like an act of financial recklessness. The environment in which selling 900 horsepower cars had seemed merely inadvisable became an environment in which it seemed indefensible. By 1974, the muscle car era was functionally over. Individual models lingered through the rest of the decade, keeping famous nameplates alive, but losing the performance that had made those names mean something. The Boss 429 had already been discontinued after the 1970 model year. Chrysler's Hemi, the Boss 429's primary technical rival, and the engine most often mentioned in the same breath, was gone after 1971. The engine arms race that had defined American automotive culture for a decade was finished. There is a particular kind of professional frustration in solving a problem correctly and watching the solution get canceled for reasons that have nothing to do with whether the engineering worked. The tunnel port program delivered on its technical promise. The heads flowed what the engineers predicted they would flow. The engines produced the power the calculations indicated they would produce. The engineering was not the problem. The world around the engineering was the problem. The tunnel port Boss 429 today occupies an unusual position in automotive history. Not quite myth, not quite complete documented record. Something in the complicated, fascinating space between the two. Surviving tunnel port heads are among the most coveted pieces of Ford racing hardware in existence. A confirmed, properly documented set commands extraordinary attention and extraordinary prices when it surfaces. The number of authenticated sets with credible provenance is small. The number of claimed authentic sets is considerably larger. Scarcity creates mythology. Mythology creates market pressure. Market pressure creates fraudulent provenance claims. Sorting the real from the manufactured requires deep expertise, or expensive professional authentication, and sometimes both.
Production numbers for the standard Boss 429 Mustang were modest. 1969 saw approximately 859 units built. 1970 expanded to around 499 additional units. A clean numbers matching Boss 429 commands serious money today. A documented 1969 example is worth considerably more. A tunnel port race engine with traceable history exists in a different category of rarity entirely, the kind of category where the word priceless starts to apply not as hyperbole, but as literal description. Here's what stays with you about this story. Ford had the engine. They had it running. They had it on the dyno producing numbers that were, by any standard of the era, extraordinary. And they buried it. Not because it failed, because the world it was built for was already changing faster than the engineers building it had anticipated, and faster than the executives approving budgets were willing to bet against. The tunnel port heads were developed during what felt, in 1968 and 1969, like the permanent peak of American performance car culture. The horsepower race seemed to have its own momentum, its own inevitability. Manufacturers kept pushing higher because markets kept rewarding higher. The engineers working on the tunnel port had reasonable grounds to believe what they were building had a future. By the time the heads were ready, the conditions that made them possible were already ending. The compression ratio reductions were coming. The unleaded fuel mandate was coming. The emission standards were coming. The insurance crackdown was intensifying. Congressional scrutiny was growing. Then the oil embargo arrived and closed any remaining debate. The executives who decided not to homologate the tunnel port engine looked at that converging set of pressures and made a rational business decision. A 900 horsepower street car, built in minimum numbers to satisfy a homologation requirement for a racing series the company was about to leave anyway, was not a sensible investment. They were probably right. It does not make the engineering achievement any smaller. It does not make the decision any less frustrating if you care about what Ford's engineers were capable of in 1970. The tunnel port heads exist. You can examine them if you ever get the chance. The pushrod tubes running through the intake ports are right there, physical evidence of what these engineers were thinking and building and solving. The program was real. The power was real. The decision to end it was real. What we are left with is an engine that lives in the space between complete history and informed speculation. Not myth, not full record. The tunnel port Boss 429, the engine Ford built, tested, nearly raced at its full potential and then decided the world was not ready for. They were probably right about that too. That is the story of the tunnel port Boss 429. If you know more about this program than I covered here, and given how incomplete the surviving documentation is, that is genuinely possible, put it in the comments. I will take corrections from anyone with primary sources. Subscribe if you want more deep dives like this one. More coming next week.